Alright, in this video, we'll explore orthogonality of vectors. You're all familiar with the concept of orthogonal vectors. We say that two vectors v1 and v2 are orthogonal to each other if their dot product is equal to 0 or the inner product is equal to 0. So the inner product of two vectors in Rn is simply v1 transpose v2. Right, and that's equal to, and if they're orthogonal, then this is equal to 0. We say that two vectors are orthonormal if in addition to them being orthogonal to each other, the norm is equal to 1. So basically they have unit length, and orthogonality, so normality says that they have unit length, and orthogonality says that they are perpendicular to each other. So one very common set of orthogonal vectors is this set of vectors, right? So the coordinate vectors, one corresponding to the x-axis, the y-axis, and the z-axis, right? And this forms a basis. This set of vectors forms a basis, and these are orthonormal vectors. So this is called an orthonormal basis. So any basis where the vectors are all orthonormal is called an orthonormal basis. And this particular basis, where one entry is 1 and all the other entries are 0, so such a basis is called the standard basis. And in particular, this is it's also called a standard ordered basis if you look at the basis vectors in this particular order. So it's sometimes denoted EI. So EI is the ith standard ordered basis vector, which is a vector with all zeros except in the ith location, which has a 1, right? So orthonormal bases are turn out to be pretty interesting, and we'll see more properties in due course. So we know what orthogonal and orthonormal vectors are. What do we mean by orthogonal subspaces? So if we are given any two subspaces v1 and v2, suppose v1 and v2 are subspaces of some vector space v, we say that the two spaces are orthogonal to each other if every vector in v1 is orthogonal to every vector in v2. So for all v1 in the first vector space and all v2 in the second vector space, v1 transpose v2 is equal to 0, right? So this is so this is what is meant by orthogonality of subspaces, right? And immediately you should see that you've already seen orthogonal subspaces before. In particular, you've seen that the null space, the right null space of a matrix, is always orthogonal to the row space of the matrix. We'll investigate that. We'll explore that in a little more detail in a few minutes, right? So this is what is meant by orthogonal subspaces. Among orthogonal subspaces, there are other special classes of orthogonal subspaces, and these are orthogonal complements. So given a vector space V or given a vector subspace V of some higher vector space, we say that V perp, denoted in this fashion, this is called V perp. So V perp is the orthogonal complement of V if it is the set of all vectors. So V perp is the set of all vectors such that these are orthogonal to all vectors in V, right? So let's assume that V is some vector subspace of another vector space U. Okay. Okay. So suppose that V is a subspace of a bigger vector space U. Then V perp is also a subset of U, and it is a set of all vectors which are orthogonal to every vector in V perp, right? So in particular, if you look at 3 dimensions, the orthogonal complement of say a plane is the set of all vectors which are orthogonal to the plane. So the dot product with every vector in the plane should be equal to 0, right? And in this particular example, what is the orthogonal complement of a plane? It is simply the line perpendicular to the plane and passing through the origin. So it may not seem obvious from the definition, but the orthogonal complement of a subspace is a subspace itself. So V perp is a valid subspace of U. And how do you prove this? So to prove this, you need to go back to the definition of a subspace. So how do you check whether V perp is a subspace of U or not? So all you need to do is show that for every scalar alpha in the field and vectors v1, v2 in perp, so take any vectors v1 and v2 in the orthogonal complement v perp, to show that v perp is a subspace, the following must hold. No matter how I choose alpha v1 and v2, alpha times v1 plus v2 should also belong to v perp. And this property is indeed satisfied. Why is that the case? Because if v1 is orthogonal to every, so if you take any y in V, the dot product y transpose alpha v1 plus v2 is equal to, again by basic properties of vector multiplication, alpha times y transpose v1 plus y transpose v2, and both these terms are 0, so this is also equal to 0. So alpha v1 plus v2 also lies in the orthogonal complement v perp, and therefore v perp is a subspace. So v perp is a subspace of U, right? So but one thing to note is that the union, so v perp is a subspace of U, and every vector in v perp is orthogonal to every vector in V. But two important things need to be noted. One is that the intersection of V and V perp are not necessarily are not empty, right? So in this case, what is V intersection V perp? So this will obviously contain the 0 vector, right? But every other vector will not, so no non-zero vector will lie in this intersection. So that's property number 1. The second property is that unlike the set complement, the orthogonal complement does not satisfy this property, right? So this is just just so that you keep in mind, you have to be very careful that V and Vperp do not partition the vector space U. So the union of V and Vperp is not equal to the vector space U. However, their intersection is just the zero vector. Right? Okay. So let's see some important properties of the orthogonal complement and how do you find the orthogonal complement. Right. So to check whether, suppose you are given two vector spaces v1, v2, right? How do you check whether v1 is orthogonal to v2? So suppose that v1 has a basis v1, v2 up to vm, and v2 has basis say u1, u2 up to un, then v1 is orthogonal to v2 if every base, if and only if every vi is orthogonal to every uj. So are orthogonal if and only if vi transpose uj is equal to 0 for all I equal to m and 1 less than or equal to j less than or equal to n. And I leave it to you as an exercise to show that if the basis vectors are all orthogonal to each other, then the spaces are also orthogonal to each other. So basically what you need to show is that not just for the basis vectors, for all v in v1 and for all u in v2, v transpose u is also equal to 0. So this is an exercise. So basically if this property is satisfied, so all the basis, so the basis vectors are orthogonal, the basis vectors of v1 are all orthogonal to the basis vectors of v2, then every vector in v1 is orthogonal to every vector in v2, right? Okay, so that is fine. So now suppose that you are given the orthogonal, you are given a vector space v1, so basically you are given a basis for v1, then what can you say about the basis of the orthogonal, or what can you say about the orthogonal complement? And for that, let's recall what we've already seen regarding orthogonal complements. So basically from definition, so we've seen that for any m by n matrix A, the row space is orthogonal to the null space, and in fact the row space is the null space, or the null space is the orthogonal complement of the row space, right? Because firstly, every vector in the null space is orthogonal to every vector in the row space, and also the null space by definition is the set of all vectors which are orthogonal to the rows of A and therefore orthogonal to every vector in the row space. And similarly, the column space is the orthogonal complement of the left null space, and the left null space is the orthogonal complement of the column space, right? Okay, so let's try to visualize this these spaces, the row space, the column space, the left null space, and the null space for a 3 by 3 matrix. So for now, let's assume that you're given a 3 by 3 matrix A whose rank is equal to 2. right? So the rank is equal to 2, and therefore the row space is a two-dimensional subspace of R3, right? So the row space is basically a plane. Right, so let's assume that this plane, of course I've drawn it like a bounded plane, but in fact it's an unbounded plane stretching out all the way up to infinity in all directions. So this is the row space, right? So it's a plane, and this is the span of the row vectors of A, right? The orthogonal complement is basically the null space, which is a line which perpendicular to this plane and passing through the origin. So this is the null space, right? So this is the null space of A. Now if you take any vector v, any arbitrary vector v in R3, then you can decompose it as a sum of two vectors. One vector which is, so the component along the null space, let's call it Vn, and another component which is in the row space, Vr. So you can always write V as Vn plus Vr, where Vn is in the null space and Vr is in the row space, right? So note that the null space is the orthogonal complement of the row space. So a basis of the null space union with the basis of the row space, it forms a basis for the entire vector space. Okay. So in this example, so we can always write any vector in R3 as Vn plus Vr, where Vn is the component of V along the null space, and Vr is in some sense a component of V along the row space. Right? Now let's see what happens if I multiply V by the matrix A. So if you take y equal to A times V, then obviously since uh, since uh, A is of rank 2, y will lie on a plane, right? So because y will always lie in the range of A, or equivalently in the column space of A, and since the matrix has rank 2, the column space is going to be a plane, right? And the left null space is going to be the orthogonal complement of the column space, which is going to be a line passing through the origin and perpendicular to the column space. So this is going to be the left null space, right? So y is A times V, and obviously y has to lie in the column space, so y will lie on this plane, right? So if you look at A times V, this is by linearity, this is A times Vn plus A times Vr, but Vn is in the null space of A, so A times Vn is equal to 0, so this is A times Vr. So basically all vectors along the null space, or all components along the null space of A, are all nulled out, they get killed, and only the component along the row space remains, right? So basically what A does is, first it transforms the row space into the column space. So it transforms this plane to this plane, and every component which is along this null space is all brought down to the null vector. So note that in this example itself, there are vectors which lie outside the row space and vectors which lie outside both the row space and the null space. So in this particular example of the blue vector v, this is neither in the row space nor in the null space, but it has components along the row space and components along the null space, right? And the components which are along the row space get preserved in some sense. So these are taken to the column space, and you can in fact get back the vector vr from the column space back to the row space, but all components along the null space get killed, right? All right, so this was a nice pictorial representation of what happens when you multiply a vector by a matrix, and this essentially sums up the subspace interpretation of a linear transformation. So this picture gives you all there is to know about the 4 fundamental subspaces and how they play a role in any linear transformation. Okay, so this was about the 4 fundamental subspaces and and we've seen that these are, so the row space is orthogonal to the null space and the column space is orthogonal to the left null space.